In this video, I'm going to discuss the setup a little bit and data handling from an open flow gas exchange experiment with a gas switching system. Before I get into data, I wanted to just show this short video of the setup that we had with the 4-channel gas switching system in open flow mode with 2 frogs that were placed in flow-through chambers on channel 2 and channel 3. Channel 1 was our reference where there was no chamber attached, just the reference gas flowing, and you can see a temperature probe here placed between the chambers. I'm just going to run this little video so you have an idea of how this system was set up. You can see that on channel 2 we had a smaller frog, and on channel 3 we had a larger frog. Having different size animals in an experiment with the gas switching system may pose some challenges in terms of flow rate selection, and I will get to that in a minute. But we've gone through the setup of the Q-Box and the setup of the software for OpenFlow in an earlier experiment. So this is just to review what a setup with 2 animal chambers may be like. So I will close that now, and here is the data file from that experiment. You're looking here at page 1, which shows raw data. There are 3 pages in our experimental files. At the bottom here are user parameters, these purple boxes, and these are parameters that have to be set up during your experiment, and before, some of them have to be set up before start of the experiment. We've got raw data here shown, CO2 and oxygen in graphs and in table format, and then flow rates and temperature of that probe, plus pressure, absolute pressure at the site of the oxygen sensor are also plotted. Before you start experiments, and we've covered this in earlier video, there are some parameters that have to be set before data is collected, and those parameters are a number of channels. In this case, we only use 3 channels with frogs on channel 2 and 3 and reference channel 1. So you have to enter this in user parameter. You can enter and change user parameters by either double-clicking on that parameter and entering the value here, or you can change the number by using the arrows with up and down right here. The second parameter that has to be set before you start your experiment, of course, is the mode. We've discussed that before, but briefly, this experiment was done with mode 0. Mode 0 is when reference is measured at the beginning of each cycle and after the last channel is measured. So in this case, reference channel 1 is measured first, then channel 2, 3, 4, and so on, and back to reference. The second mode that's available is mode 1, and I'll change this here to show you. Mode 1 is when reference measurements are done after each channel with the sample. So you would measure channel 1, which is your reference, then 2, back to 1, then 3, back to 1, then 4, and so on. Mode 0 is recommended for measurements when you have changing background levels, and you need to monitor those background levels more frequently. But the disadvantage of mode 1 is it takes longer to complete your experiment. It takes more time to measure all the chambers. So mode 0 is recommended if you don't have these issues and you want to get through your experiment in a timely manner. And the third parameter that has to be also set up before starting the experiment is dwell time. Dwell time is the time period that the system is dwelling on individual channels that are being measured. So each channel is measured for 3 minutes. In OpenFlow, all channels have gas flowing through the chambers, and for 3 minutes each channel is measured. And while the other channels are not being measured, the gas just vents through the vents of the gas switcher. So these are all three parameters that have to be set before the start of the experiment. There's also event time, but this parameter can be set after data has been collected, and we'll cover that a little bit later. You will notice in this experiment here that we were using different flow rates in channel 2 and channel 3. Channel 1 and 2 were both around 250 mils, and channel 3, which had the larger frog, was set to 450 mils. This was done for sort of demonstration purposes to basically show how larger animals will obviously produce higher amounts of CO2 and consume more oxygen than smaller animals. So to bring the levels of CO2 and O2 within the same range, we increase the flow rate on channel 3 compared to channel 1 and 2. This is something to keep in mind when setting up your experiments, trying to figure out the ideal flow rate. It's important that the flow rate is high enough so your differentials of CO2 and O2, which you will see on page 2 of the experimental file, that these differentials are significant and measurable. In this case, we're looking at about 200 parts per million. It's important that the levels of CO2 that are being measured do not reach 2,000 parts per million, because the CO2 analyzer has a range of 0 to 2,000. So anything higher than 2,000 will not be measured. So if the levels of CO2 that you're measuring are creeping up close to 2,000, increasing the flow rate is a good idea, because then you will bring your levels of CO2 down. So the signal, there's an inverse relationship between the signal that's being measured, CO2 and O2, and the flow rate. So for very active animals, you may want to keep your flow rate higher, and for less active animals, you may have your flow rate lower. So the lower the flow rate, the higher the signal. The higher the flow rate, the lower the signal. However, one has to keep in mind that when you decrease the flow rate, for example, in a less active animal, that you think about how long is your dwell time, because you have to ensure that the flow rate is that your dwell time is long enough at your lower flow rate to flush your chamber fully, at least 4 to 5 times. So you have to look at the volume of the chamber, the flow rate that you're hoping to use, and then dwell time, and adjust it accordingly. So the you flushing your chamber in a timely manner, and you're flushing it multiple times to get sort of steady state levels of CO2 production and oxygen consumption. In general, it is recommended that you use the same size animals in a system, multi-channel system like this, and it's recommended that you use the same flow rates, or similar flow rates, I should say, that are appropriate for that size animal, because you can only select dwell time for the whole experiment. It's the same dwell time for all chambers, so it's important that your flow rates are not dramatically different, because then the dwell time may be not appropriate for the different flow rates. The other thing that I'd like to mention here, I'm just going to stretch this graph with CO2. I want to just explain some of the symbols here that you're seeing and the data itself. So first of all, the symbols, these are flags that software uses to indicate when to switch from different chambers. The red cross represents when the switch occurs from reference to the next channel. So any data that is collected before you see this red cross is coming from the reference. So again, here, this is the data that has been collected from channel 1. You will see that at the beginning there, you're still seeing some CO2 being flushed from the previous chamber, and that's something to keep in mind. There's always a flush time involved at the beginning of each channel before you're actually measuring gases from that channel. The red dots represent when you switch from individual channels between 2 and 4 in this case, in a 4-channel system, or 2 and 8. Because we only had 3 channels in this experiment, we have channel 1, which is the reference, channel 2, which has a sample and it's represented by the red dot, and channel 3 here, you see this orange triangle. Orange triangle indicates the end of the cycle, so the very last channel that's being measured before returning to reference. So channel 3 is actually our end of cycle orange triangle. So we're measuring channel 2 between the red dot and this red cross, and we're measuring channel 3 between this red dot and the orange triangle. And each cycle is represented by these orange triangles. So here you're looking at in a single cycle. The other thing to mention here is this dark line here represents our reference CO2 readings, and we're actually measuring reference in these sections between the triangle and the red cross, but the data in between, when reference is not being measured, the reference is extrapolated from these 2 measurements. So the reference data that's used to subtract from the sample CO2 data is extrapolated from the measurements of reference at the beginning and at the beginning of each cycle. One more thing to mention is that our oxygen analyzer measures oxygen as in kilopascals. It also has a pressure sensor which measures absolute pressure at the site of the sensor, and then the kilopascals of oxygen measured are corrected for any changes in pressure, and the P-corrected data in percent oxygen is plotted on the graph, and it's shown in this meter as well and in the table. So, okay, so we can now move to page 2, where our differential data is plotted. So this is the data for CO2 and O2 where the reference levels have been subtracted. And you can see, again, here we're looking here at data of the single cycle with here reference data, which should be 0. We have some noise here in the oxygen signal. We have you can see the differentials of CO2 and oxygen about 200 parts per million, which is fine. So before we can proceed here, there are 2 parameters, user parameters here that we should set up. The first one is the O2 delay. The O2 delay is a parameter which basically aligns the CO2 and oxygen signals, which may or may not be aligned depending on the flow rate of the system, the volume of the chambers, and the oxygen analyzer is in a series behind or after the CO2 analyzer. So CO2 is measured first and oxygen is measured second. So if flow rates are low and one may find that the oxygen signal is being detected a little bit behind CO2. So before any calculations are done by the software, it is important to make sure that the signals are aligned. And to align the signal, we use this O2 delay parameter. But first we have to find or activate the examine function. If you go up to the menu at the top here, if you hover over these icons, you can see what they do. Examine is this one, tangent, statistics, and so on. You can activate it either through this icon here, or you can go to the menu, analyze, and select examine here directly. What happens is you'll see this line up here, and you can use this line to check the alignment of your CO2 and O2 signal. And the best place to do that is by looking at individual sort of peaks or deflection points where both oxygen and CO2 are clearly showing a deflection. It helps to actually zoom in on the data because if you're looking at this data close up, it's you can see the individual points. I'm just going to adjust this here to about 18. And now we can kind of bring this examine here, examine line and see, and you can see that the data is pretty much aligned. You know, you don't really see a misalignment in this particular data. However, if there was misalignment, you would adjust your O2 delay here and watch the data, you know, go back into alignment. So I've adjusted it by 1 point, and I actually misaligned it by doing it. So I'm going to go back to 0 because this particular data set does not need any alignment. It's already aligned. I'm going to close that now here. And the other parameter that you want to adjust here is the event time. I mentioned that earlier. Event time is usually about 1/3 of the dwell time. So with 3 minutes, going back to raw data here, with 3 minutes dwell time, event time of 1 minute is sufficient. And what the event time does is it basically tells the software how much of the data from the point when you switch to the next channel, so at the end of the dwell, it needs to be used in calculations because this software will report a single point for each dwell, which is an average of the event time data. So going backwards here, you know, you select about 1/3 of your data, which in these cases is about a minute, and that is the data, CO2 and O2, that are used in calculations. And you know, we hope to see, you know, fairly steady state data at the beginning of a switch. You don't want to use this data because things are still flushing from the previous channel. You know, so we're looking at data at the end, and that's about, you know, a minute in this case, which is used in those calculations. So once we have set up these two parameters, then we can go to page 3, which is the summary page, and this is the page where the calculations are done. The calculations are explained in this text box here, how they're done. The formulas are shown here. The manual also explains this, you know, with the open flow system, gas switching system that's using Q-Box RP1LP. The flow rate is measured downstream of the chambers, and the appropriate formulas are used for those calculations. So in the summary data, you will see the graphs of the metabolic parameters, VCO2, VO2, and also RQ, which is the ratio of VCO2, VO2. RQ provides information about the diet of the animal, you know, and other physiological states. The VCO2 and VO2 are provided in microliters per hour, but you can see these numbers are pretty high for these frogs. They're quite active, so one may want to adjust them into different units of mils per hour, but that can be done after you've moved your data or copied your data into an Excel spreadsheet. So this table here that you see shows the VO2 and VCO2 data for each channel at the end of that table. So VCO2, VO2, and RQ for channel 4 will not be here because we didn't have that channel activated. Here you can see data point for channel 2, and you just have to scroll up and down here to find these appropriate spots, time points when this data is calculated. Oh, I just passed here channel 3. Okay. So as I said earlier, the software calculates a single point for each dwell time, and that's the points that are being graphed here and shown in the table. Now one can then copy paste this data into Excel. For example, I'll show this by just going Control C in Logger Pro, and then you open a new workbook and Control V to paste your data. The titles of the columns are not come across, so you have to type them in: BCO2, BO2, and RQ. And you just copy and paste the data of interest, into your spreadsheet here, and then, do appropriate analysis. Or the other way is you can go into File and Export As and select CSV, and then put that data in whatever folder. Select the folder. So this is OpenFlow exported data. Okay, and then you can open that data directly in Excel, and you will have to convert it, of course, and you will see all the data come across. You will see all of the raw data, which is going to be in the first initial columns: CO2, O2 pressure, flow, temperature. You will also see all the data that's required for the control of the system, for the control of the gas switcher, for organizing and sorting of the data into individual channels at the end. All those calculations will come across, and if you scroll right to the end where our channel 2 data and channel 3 data is, you can then do the same thing by scrolling down to find the individual data points. Here's our channel 2 data points, and here's channel 3 data points. And again, this Excel spreadsheet will require some organizational work to combine the summary data into a smaller table and then be useful for any kind of statistical analysis later on. So that kind of covers more or less what one can do with this experimental file. Once you've obtained some of this initial data from a trial run, you can determine the best dwell time, the best flow rates, the best event time for your experiment. You would save that file, and then you can clear this trial data and open the file, clear this trial data, and then use that as a template to run your experiment for the actual experiment for the period of time that you need to do. And what we would recommend is that people save their data frequently, okay, by going to File, Save As in a specified location. And that's important because Logger Pro does not automatically save any of the experiments. They have to be saved manually. And if you're running your experiments over a few hours, it's a good idea to save periodically. And if you run your experiments over a few days, then I would even recommend that you save your data at the end of each day and close the file, and then, or keep the file open, save the data under a name for that day, then clear the data, save it again under a new name for the next day, and restart the experiment. So basically restart your experiment every day so you don't end up with a one big experimental file with a lot of data, which is then more cumbersome to manipulate. And also, in case something happens, you're not losing all the data in case there's some power outage, and the computer goes down, whatever. It's a way to make sure that your data is backed up and saved.